Hey guys, why was I calculating all of these pictures and numbers? What's going on? And like, why does it say stop and continue? Let me tell you about it. I recently posted a video where I talked about a process where you randomly, kind of uniformly between 0 and 1, you choose random numbers and you continue every time their sum is less than 1. But as soon as the sum of the numbers you have is 1 or more, you're going to stop. And so the question was, how many rounds would you expect to last? And we had to calculate the probability that we would stop, say, after 3 rounds or 4 rounds, things like that. Now I've color-coded everything and I want to show you some pictures. I want to start by focusing on what happens when we continue. Every time we continue, it must mean that the sum of the numbers we've chosen so far is strictly less than 1. And I'm going to draw some pictures to illustrate what's going on. If we've only chosen 2 numbers and their sum is less than 1, we can think about that as points in the xy plane, and we get this purple triangle here. And I bet you know what the area of a triangle is. It's just 1/2 base times height. And so the area of this is going to be 1/2. When we move to the 3-dimensional case, we have 3 numbers whose sum is less than 1, and we get this pyramid shape here that I've shaded in green. Now notice that the base of that region is exactly the same as that purple triangle we just saw. That's because if the sum of 3 numbers is less than 1, then the sum of the first 2 has to be less than 1 as well. I'm going to fill in the base of that pyramid as having area 1/2 because I know a formula from geometry that says the volume of a pyramid is 1/3 the area of the base times the height. And so if I work this out, I get the number 1/6. Now is probably a good time to review what happens with pyramids in general. So I've drawn these pictures to kind of illustrate the pattern that shows up when you find volumes of pyramids. Now as we get in higher dimensions, we have to change, say, from area to volume, and when we're in 4 dimensions, there's actually something called 4-dimensional volume. You can use calculus to prove all these formulas, but one thing that I hope you notice is that as the dimension increases, instead of dividing by 1/2 or 1/3, we're just dividing by whatever the dimension is. But we always have this familiar thing that it's the area or volume of the base times the height. So if I'm continuing when I have 4 numbers, it means their sum is less than 1. I can't really draw in 4D, but we're going to get a similar picture as we had over here, where we get some sort of pyramid that has the same base as what we had in the previous case. And I've already filled in that that base has volume 1/6. And so according to the formulas we just saw, because we're in 4D, the volume will be 1/4 times that volume of the base, which is 1/24. Now I'm going to fill these numbers in a table, and maybe you've already noticed a pattern. Each time we continued, we noticed the probabilities of 1/2, 1/6, or 1/24. In general, this is 1/n factorial, where n is just the number of numbers that we've chosen. So now we're going to put everything together into this algorithm and see if we can calculate the probability of stopping. So we've got our first 2 numbers. We're either going to stop or we're going to continue. And we just worked out that all the continue formulas are really nice. Like that first one is just 1/2. Well, if half the time we continue, how often do we stop? Well, it's got to add up to 100%. So we get 50/50. So I'm going to mark that in here. And now we're going to delve inside and see what happens in that continue step. So say we've chosen our 3rd number. We're either going to stop or we're going to continue. But we know the formulas for all of the continues. So in other words, the probability of continuing is going to be 1/3 factorial. And so if you keep in mind that this whole thing only happens 1/2 of the time, then the probability that we stop has to be the difference of the whole minus the part. And that's what I've got down here. Now you might be tempted to simplify this, and I did down here, but we're actually going to keep it unsimplified when we put that in. So we just filled in the probability of stopping at round 3 as 1/2 factorial minus 1/3 factorial, and now we can break down this green continue into its 2 parts, right? So this whole green thing here is going to have probability of happening 1/3 factorial, and we know the probability of continuing is just going to be 1/4 factorial, right? That's the pattern we did with the pyramids. And so now what's the probability that we stop? Well, again, it's just going to be the whole minus the part. And so you're probably noticing a clear pattern here. In fact, I went ahead and even changed this 1/2 at the beginning to, it's the same thing, 1/1 factorial minus 1/2 factorial. And we see a very, very beautiful fact that we could, of course, prove rigorously with induction. And this allows us to calculate, ta-da, the probability that we stop exactly in n rounds is this beautiful difference of two fractions involving factorials. I hope this adds some clarity to the video I posted the other day. If you have questions, please let me know. If you like this content, I'd love it if you could subscribe or tell a friend about this. I'd love to share math with everybody.